for me?
Okay, okay. So in the last two lectures, I introduced some of the techniques and conventions and all that to some of the technology that we are going to use today to compute the endpoint string amplitude at tree level that we are going to start computing today. What we want to compute is the endpoint amplitude, and with the color ordering like that. And this morning, Freddie told you that most people compute the color ordered amplitude without even mentioning that it's the color ordered amplitude, and that's what I have been doing so far. But now I just wanted to mention that, just to be Freddie compliant. So we want to compute this amplitude that can be the prescription to compute it is this one. We have seen this a lot of times already. So n minus 2, and then v n minus 1, position 1, v n position infinity, and the correlation. And in the last lecture, I told you what are the vertices, and the vertices look like they are given like this, x and theta, and then this is the unintegrated vertex, and the integrated one is this one. Right, and the strategy to compute the amplitude will be to use the OPEs, because this guy has conformal weight 0, and these operators here too small. Oh, I thought I was writing big, but okay, h equals 0. Yes, okay. So, but these guys here, they have conformal weight 1, and they are going to be eliminated from the path integral, the correlation function, using the OPEs. And so I will just write a few of the OPEs that we are going to use. The first one will be pi m of z with an arbitrary superfield, but I will write it as w, as v, say, and with a label denoting the particle label I, that is momentum m I v I. It's a simple pole, and then the other OPE will be this one. That's the covariant derivative in x and theta superspace, and the third OPE will be right. So I'm basically writing the OPEs of this guy, this, and that one, because at tree level, at least for today, this guy there will not contribute. So these 3 OPEs will be enough for today. Okay, so right, and then I also mentioned that, well, and the superfields today, they're going to be, well, every day. So, but so a superfield for me will be expanded in terms of the plane wave. So it will be something like that, and these superfields, the theta expansion of these superfields, I told you about in the last lecture. So those expansions are the ones that are going to appear there, and then the x dependence is just in the plane wave factor. Right. And then in the last lecture, I also mentioned that once you do this, you use the OPEs to integrate out the non-zero modes of the variables. You will still, in the end, have an expression containing 3 pure spinors and some numbers of thetas that come from the superfields. And the prescription to integrate to do this remaining integral is say I'm going to define it as the pure spinor bracket prescription. It's I'm just repeating a bit of the last lecture just to try to be complete, self-contained today. But okay, so this is the prescription that will allow you to eliminate everything, including the 3 zero modes of the pure spinor, right? So you may look at this and you think that, well, it's going to be a complicated computation if you want to compute, say, the 1,000 point amplitude like this. But in the last lecture, I also mentioned that we found that there is the notion of pure spinor superspace, which is a superspace that depends on x, theta, and lambda. And so in this superspace there is an interplay between various facts that are present here. So the first one is that we have the 10-dimensional Superang-Mills equations of motion at our disposal, and then they are written in terms of the covariant derivative. And then another fact is that the BRST charge is simple, and it also contains the same covariant derivative that we see there. And this guy here, well, it's the lambda 3 theta 5 shorthand. There is a nice cohomology associated to the measure lambda 3 theta 5. And today we are going to use these facts to enable us to compute the amplitudes. And so any questions about the setup?
What is VI?
Oh, VI is the unintegrated vertex that describes particle with label I. So in this case, VI, and then so this superfield will contain the polarizations and momenta for particle with label I. So yeah, so these numbers here are the particle labels. Any other question? Yes.
What do I use instead of the 1? Am I just redefining?
Oh well, in fact it's more convenient to set this to 2880, but it's your choice. It's just a normalization convention.
In what sense is it a measure?
Oh, in what sense it's a measure? Well, it's something that is used to integrate the variables that remain in the correlation. So yeah, it's a measure. Any other question? Okay, so let me just write down the equations of motion again, because I wanted to do this in the coffee break, but the blackboard was occupied. So I'm sorry that I'm writing this now. Okay, so these are the equations of motion. So equations of motion, 10-dimensional Superang Mills, and by the way, this is in 10 dimensions, and Superang Mills theory in 10 dimensions, upon dimensional reduction, gives rise to the lower dimensional Superang Mills theories. In particular, the one that is very famous, the n equals 4 Superang Mills theory. So yeah, there is a well-defined procedure to go from this description to that description doing dimensional reduction. So in some sense, I think it's nice to have an understanding of 10-dimensional Superang Mills theory, because it's the mother of all the other lower dimensional Superang Mills theories. And in particular, well, these equations here are simpler. But anyway, okay. So let's start with the first non-trivial. Well, the 3-point amplitude is basically there is basically nothing to compute. It's just this one, right? Okay, and I forgot to mention the behavior of the vertices. So QV equals 0. So from this result, you can see that the integrand is BRST closed. So it's BRST closed. And I just want to note that sometimes I use the same notation to denote that we are doing a path integral, and after we remove the conformal weight one variable source in the OPEs, the same bracket is used to denote that this is the prescription to integrate out the zero modes. So in that case here, it's this bracket here is the one for the lambda 3 theta 5 measure, and the context should make the use clear, because what's inside here has conformal weight 0. Yes, so conformal weight 0. So yeah, so the other use of this bracket is when there are conformal weight 1 variables inside. Okay, so let's go to the 4-point function, and this is so V2, V3, V4, where the position 1, 3, and 4 are 0, 1, and infinity. So let's see what we can do from this expression, and that will lead us to the patterns that are going to be uncovered today. Oh, it's V. So this one is U. V1, U2, V3, V4. So okay, V. I will write like that. And yeah, well, sorry about that. Okay, so from this expression, we know that we need to compute just one type of correlator or OPE between VI at position ZI and U2, and yeah, in this case U2 at position Z2. Right, so and this guy, well, and there is something else here, which is, well, it depends on which eye you have, but it's BRST closed. So let's do this computation and see what we have, what we get. Okay, so U2, let's just write down the answer. So V1, so let's compute with V1 at Z1 and U2 at Z2. And if you use the OPEs here, you will get this answer. You will get minus Z12 minus K1 dotted to A2 M V1, and then the other term is minus W2 D alpha V1, and the other term is plus 1 or minus 1 over 4 A1, and then multiplying F2 Fmn. Right? Okay, so this is, let's call this is term number 1, number 2, and number 3. And you can see that 1, 2, and 3 here map with the use of the OPEs 1, 2, and 3. Right? For example, the OPE 1 simply picks the momentum 1 of the V1 vertex, which is there, and then A2 here comes from the integrated. So yeah, so term 1 comes from this part, term 2 comes from this one, term 3 from that one. So this result is correct, but it's not convenient. It looks, it's not optimal, but let's see what we can do. Let's look at term number 2. So term number 2 is that one, and you can write it like lambda beta U1 beta, right? And now we have this term here, and we use the equation of motion 1 over there, and this becomes minus del beta A1 alpha plus gamma m So now you see what happens, because lambda beta contracts with d beta, and you get minus W2 alpha, and then lambda contracted with d acting on 1 alpha, and then minus just that other term here, minus gamma alpha. Oh, and oops, I forgot the right. So, but this is the BRST charge, and one of the things that I emphasized was this part here. We now have the BRST charge, and we can use the cohomology property of the pure spinor measure, meaning that we can integrate the BRST charge by parts, because this guy is inside the pure spinor bracket. So let's do that for that term and see what we get. So let me just write, emphasize this. The cohomology means that the pure spinor bracket of Q of anything is 0. So that term minus W2 alpha Q is this is inside the bracket. This is can be written as Q of W2 alpha 1, right? Because Q1 W2 is fermionic, and but now we need to add the action of this. So let's plus plus Q of W2 alpha A1, like that. I decided that I'm not really going to keep track of whether things are minus or plus, but it should be easy to fix that. So and now what is this? This is lambda beta del beta W2 alpha, and now we use the equation of motion 3 here, and that becomes plus 1/4 lambda alpha. So in connection with that contraction there, so it's okay. So this guy, well, I just said that the correlate the pure spinor bracket of something BRST exact is 0. So this is 0, and this one becomes plus or minus 1/4 lambda gamma mn A1, and yeah, it's okay. Oh, and okay, I'm sorry. I forgot the F2, because the equation of motion of W gives you F. So and you see that this term here, which was term number 2, now cancels term number 3, and what remains are this term and this term here. So let's summarize the result of the calculation. So V1 U2 is minus Z to 1, and then V1 K1 dotted to A2 plus which is more convenient than these 3 terms over there, because, for example, there is no covariant derivative anymore, and this term here is not convenient to the study of the BRST variation of this term is not particularly interesting, but this result here is much more convenient. So let's give this a name. So this defines, let's define this as L to 1, right? And well, we used the fact that we could integrate the BRST charge by parts, so this should be understood that it's inside the bracket with anything outside. Okay, so that's the first indication that you can use cohomology manipulations, and in connection with passing from the simple form of the BRST charge with the connection with the equation of motion. But you can do more, because now let's see what happens when you compute the BRST variation of this guy. So the first term is minus V1, because V1 is closed, and then Q1M lambda gamma M2 plus momentum 2 v2. I use the equation of motion 2 here in this factor there. And now, well, I didn't tell you, but before, and I should, but you can show that the pure spinor constraint implies that this is 0, and the equation of motion of W implies that this is 0. And well, it's easy to see because you will get something of the form lambda gamma m and then lambda gamma rp with another lambda here and then rp. But this combination here is 0. I mentioned this in the last lecture, simply because lambda is a pure spinor. So this term there doesn't contribute, and you get again minus and then the same thing here with 1 plus okay, so this term here is 0 because I also mentioned in the last lecture that whenever you contract, you have this combination here for two pure spinors. This is 0 no matter what you contract with alpha and beta. So this guy is 0. So let's do this. And this guy cancels this one. Why? Because V1 anti-commutes with W2 because they are fermionic. So you cancel this with that, and what you get in the end is momentum 1 minus momentum 1 momentum 2 V1 V2. Whoa, okay, so this looks nice, right? It's a simple answer. Let's try to understand why we got this. The L21 was defined as the simple pole of the OPE of V1 with U2. So let's compute the BRST variation of this guy like this. And this one is BRST closed because of the two properties that are written there. And you get minus V1, and then the BRST variation of U2 is del V2. But now del V2 is using the chain rule is this one. Momentum 2m V2 and then plus del lambda alpha A2 alpha. But this guy has nothing to contract here because the OP of lambda with lambda is 0. So this guy will not contribute anything. The same thing here. This has no singularities with that one. So the only term that remains is this one. And now you can see that when you compute the OP of pi m with V1, you get the momentum 1. So the result here is plus. Yeah, it should be minus, but I think it should be. Okay, my handwriting degenerated. So we have an understanding for why this equation is true. So let's try to do this recursively now, because we know in the background that we want to compute the endpoint amplitude. So we should try to find a recursion somewhere, because you cannot simply go to 4 points and then 5 points and then 6 points, and there is an infinite number of amplitudes to compute, and you will never finish. So so let's see what happens if you compute the BRST variation of L2 U3 with L21. So this is del V3 L21 plus U3 and now S. Okay, now let's momentum 1 dot to momentum 2 V1 V2. And now we use the same trick as before, that we wrote this guy in terms of pi m, and then pi m picks the momentum of this operator here. But the momentum of this guy is momentum 1 plus momentum 2. We just collided the two vertices. So this guy is minus momentum 1, momentum 2 dotted to momentum 3. But the notation here is momentum 1 plus momentum 2, V3 L21. And then this guy here becomes plus, by using the definition of L21, we now have, so this becomes L31 V2 plus V1 and then L32. So we see that we get the same type of objects that we started with. So and okay, and then you define, okay, this is L2131, and then you just define it. You just found that the BRST variation is that one. Okay, so I forgot to mention something about L21, actually. Let's let's see what happens with computing the BRST variation of L21 plus L12, so the symmetric part of L. This is minus momentum 1, momentum 2, V1, V2 plus V2, V1. So this is 0 because the anti-commute. So you learned that the BRST, the symmetric part of L21 is BRST closed. But I just mentioned to you that the momentum associated to this superfield is momentum 1 plus momentum 2. So in particular, the conformal weight of this guy here will be proportional to the momentum squared, and this is proportional to 2 times k1 k2, and that is generically different than 0. So what we found here is that there is a BRST closed object with conformal weight different than 0, and there is a theorem that says that this guy is also BRST. So it's BRST closed, right? And has conformal weight different than 0, so it's BRST trivial. well, so L21 plus L12 will be Q of something else. Is that okay? But okay, so let me just mention the argument there to check, and let me write down the answer actually. So the answer here is that it's the BRST variation of A1 dotted to A2, and this you can check using the equation of motion. So I just mentioned that a BRST closed object with conformal weight different than 0 is BRST trivial. And okay, so how one can prove this? So let's say Q of phi is 0, and the conformal weight of an operator can be computed by L0, where Lm is the Fourier component of the, well, it's related to the Fourier decomposition of the energy momentum tensor. So that's how you compute the conformal weight of a field. And you also need to know, okay, so this is just a parenthesis. It's not really, because I'm saying things that I haven't defined. But in a topological CFT, you have a B ghost, and that satisfies this equation, that Q of B is equal to the energy momentum tensor. So in particular, Q of B0 will be L0 if you do the Fourier decomposition there. So what we know from here is that now if age is, so if age is different than 0, then you can write phi as Q of the B0 phi over age. So you just proved that a BRST closed guy is also BRST exact. So that is why you are guaranteed to find the solution to this equation here. But why I mention this? Because we are in the setup where we care about the cohomology of our objects. So, and we just proved that the symmetric part here is BRST exact. So we don't want such things. So we are going to define a new object by subtracting the BRST part of the BRST trivial part of the object. So, and well, okay, so this becomes the anti-symmetric part here. And so now we see this V12 there. This guy is truly in the cohomology. Not in the cohomology, but it's a good cohomology object because it doesn't have any BRST trivial components. When did I start? Okay, so all these detailed computations were meant to make you believe that we can also find combinations of these objects that are in the BRST that are BRST closed. So they will also contain BRST exact parts. So you must remove them. And once you do this, I'm not going to show that, but I just wanted to do this with very with lots of details for L21, just to make you believe that this is going to happen also at higher orders, and it does happen. So in the end, so you can redefine this guy by subtracting BRST exact components, and you will find an object denoted by V123. And once you do this, well, you can do this recursively, and you will find so now I think there is no alternative. Okay, can I use this one directly? Like this? Oh. More or less, yeah. Yeah, well, it's not perfect, but nah. Not good. Okay, so once you do this, you will find the following patterns. You will get something. Wow, this is the statement that we are familiar with from the beginning, and so this one we just proved it. And the next one, you will get momentum 1 dotted to momentum 2, and then V1, V2, 3 plus V1, 3, V2 plus momentum 1, 2 dotted to momentum 3. Okay, I realized that it's a bit small. and you can go on like this. Say V1, 2, 3, 4 will be V1, V2, 3, 4, and then plus other terms, and then momentum 1, momentum 3, V1, 2, V3, 4, plus other terms, and then momentum 1, 2, 3, momentum 4, V1, 2, 3, V4, and that's it. And just following the recursion idea there and subtracting BRST exact components, you find a structure like this. And so the formulas, if you want to follow them, I think it's in this paper. But so okay, so there is this BRST algebra, and these fields there also based on symmetries. We just know. We just saw that V12 is minus V21 simply because by definition we got just the antisymmetric part, and V123 plus V231 plus 312, that's 0, and in addition the first two labels of this guy inherit the symmetry of the lower rank. So, and then the next one over there satisfies this symmetry here, V12 4 3 plus V3 4 1 2 minus V3 4 2 1, that's 0, and there is a general formula for that you can look at the paper if you are interested. But so this is the antisymmetry, right? So antisymmetry, and this is the equivalent of a Jacobi identity, and the higher guys here don't have famous names associated to it, but they are the generalizedly symmetries. And you can convince yourself that the symmetries of these objects here with P labels, it's equivalent to a symmetry of a contraction of structure constants like this. Say A2, and then 3, A4, label 4, A5, and until F, A, P minus 1, and then label P, and then another extra label here just to complete the. So the symmetries are equivalent. As it takes some time to convince yourself, but it's true. And what is nice about this contraction of structure constants? These structure constants are the same ones that you get once you dress this guy here with color and P labels, and then you let the last leg here be off shell that corresponds to that one. So you can, and there is a nice structure that is here, which is related to the BCJ identities, simply because of the definition of these V's. They satisfy the Lie symmetries by magic, I think, because once you subtract the BRC trivial components, then you realize that these symmetries are there. So, but I won't have time to say anything about these, but it's there. The relation is, well, it's related. So if you know about BCJ identities, you can be happy. Okay, so but we have these objects V with generalized labels. So let me introduce a notation, say with a multi-particle label like this with P labels. I can say that this is V of some B, and this B here will be this string there. But so this is a convenient way to refer to higher rank V's. But we have this generalized V with a multi-particle label, and we know that, well, you can define this guy as something like this, where you define a generalized A alpha superfield, because you just look at this, and this one is the single particle instance of this definition here. But then you can ask yourself, okay, so you have A alpha with a generalized multi-particle label. What about the others? And by others, I mean, what about these guys? Do you have generalized versions for these superfields, and how do they look like? And the answer is yes. And to see this is a bit more complicated, but I will just sketch how you get those higher the other classes of superfields. The idea is that you compute the single pole in the OPE of two integrated vertices, and you define these as U23 over, say, well, 3 here, and then plus double pole. But I won't discuss these double poles until perhaps in 2 days in my last lecture. But so and then you do this CFT computation, and then you simply read off the components there, because you can write this guy here as del theta 23 A alpha, and then pi m am 23, and so forth. And then from the CFT calculation, you just read off the components associated to each conformal weight Born variable that you get, and in doing that you find the explicit expressions for these guys. And I want to write it down, at least one of them, because Well, let me not write down the realization, but let me write down the equations of motion that these generalized guys satisfy. Say, let's do it with label 1 and 2. And there are three other equations, but I won't have time to write them. But I just want to emphasize the structure here, because look at this equation here and that equation there, the first one. It's essentially the same structure, except that you get this contact term. But this contact term is precisely the one that we saw over there when we computed the BRST variation of V12. Why? Because let's do it here. Let's contract this equation with lambda alpha and lambda beta. So if you do this, you get 2 times the BRST variation, the BRST charge acting on V12 is equal to this part here cancels by the pure spinor constraint, so you get 0, and then you get 2 times momentum 1, momentum 2, and V12, which is the equation that we had there. So the idea here is that we are doing a CFT computation, and we are striving, we are trying very hard to find relations and patterns in the results that you compute, and this is such a pattern. Once you start doing these computations, you will find the same type of equations that you had for single particle case, but now with the addition of some extra with the contact terms. So these are generalized, generalized super-Yang equations of motion, and they turn out to be very, very convenient to understand the structure of the equations of the computation. I have like 10 minutes or. Yeah? Okay, what can I do in 10 minutes? Any questions? Yeah, well, yeah. Let's summarize the only amplitude that we computed today. It's the 4-point, but tomorrow, in 2 days, we will compute an infinite. Well, the rest. So So okay, we started with V1 U2 in the context of the 4-point amplitude, and if you finish the analysis, you will find that the 4-point amplitude is the integral of dz2 and V1 2 Z1 2 V3 4 plus V1 V3 2 V4 over Z3 2, and then multiplying the Koba-Nielsen factor here. And I didn't mention this, but the Koba-Nielsen factor is obtained by computing the correlation of all the plane waves in your correlator. So there is a Koba-Nielsen factor here. And okay, so this is the result of the 4-point amplitude using these new objects. And in the last lecture, I'm going to show how this structure generalizes to endpoints. But before doing that, I will write down the 3-level Superstring-Mills scattering equations, scattering amplitudes, which then you can find from setting the alpha prime parameter here to 0. But we are going to do it in a reverse order. We are first going to compute the endpoint Superstring-Mills amplitude in field theory, and then after that we are going to compute the string amplitude and identify the result that we stated here in the computations. So I guess it's time to stop. Well, and these ideas also work at loop level, because you have the same vertices there. So whatever you learn here, it will be useful for loop amplitudes. But I just decided to do 3-level just to go very slowly and just to, yeah. But that's it. Oh, it's well, it's a bit more complicated, but not that much, because, for example, I will just write one example here. Say you want to compute this amplitude, the object associated with this cubic graph in terms of the BCJ language, and the result that you will find is something of this form. I didn't tell you what this T 3, 4, 5 is, but because I simply didn't explain anything about the one loop prescription, but you see that this V12 is associated to this guy here in a very intuitive way. So well, just that I can be, for completeness, F5 MN. This is the definition of this object here, and it is inspired by the zero mode saturation pattern in the one loop prescription. And for example, say you want to compute this guy here with 4, 5, 6. Then you go here and then 1, 2, 3, something like that, and then 4, 5, 6, and these are the patterns that we are seeing. 10 dimensions, yes, but okay. So, for example, Well, suppose you want to start simple, and you want to find the gluon scattering amplitude here. It's exactly the same result when you expand these in components in 10 dimensions. You get a bunch of polarizations contracted with momenta, or momenta contracted with momenta, and things like these in 10 dimensions. And the result is exactly the same as in 4 dimensions for gluons. 3 level, yeah. No, okay, no. Well, we are talking about one loop here, and the prescription to compute this correlation here is independent on the loop order that you are looking at. It's just the lambda 3 theta 5 measure. That's universal. That's you just do the gamma matrix algebra and you get the answer. And that can be automated, and I have automated that. It's just that you press enter, wait 1 second, and you get the answer. The answers, though, they become bigger and bigger, because simply.
I'm not asking about one loop in 10 dimensions. I'm asking about the reduction from 10 dimensions to 4 dimensions.
Yeah. So.
The level of an integrand, the result. I mean, a priori this is symmetrical. Particles in the loops are flowing in 10 dimensions, like this dimension.
Well, what I'm saying is that compute the thing in 10 dimensions first, and then do a dimensional reduction in the answer to get what you get. Well, you can do that. I don't know if that's obvious or not, but yeah. I think 2 months ago, this has been done for 2 loops, 5 points, both n equals 4 and n equals 8 supergravity, because the n equals 4 parameterization here was in terms of this language was shown to satisfy the BCJ condition, so you get n equals 8 for free. What you are seeing here is that the string prescription and this BRST organization of the calculation is providing a very intuitive understanding of field theory amplitudes as well, not just string theory. Okay, so now you're starting to ask complicated questions, but
So simpler one. So if the statement that if you compute this amplitude equal on 10 dimensions,
yeah.
It's exactly the statement that equals for in 4 dimensions. You just have to put in 4 dimensions.
Yes.
Even at the loop level. But in 10 dimensions, you're doing like 10 dimensional loops.
Oh, okay. No, yeah. I forgot to say this guy here is that there is a loop momentum integral associated to this guy. It's something. Yeah, it's the kinematic part of the integrand, and then you have the loop momentum guys here. But these integrals can be, well, you can. Yeah. It's the integrand, yes. But yeah, okay. So and once you have the integrand, then you can study, for example, the ultraviolet divergence by just changing the definition of the dimension here, and then you check that at one loop the first UV divergence will appear at 8 dimensions, and you can study the things coming from 10 dimensions and looking at all lower dimensions. But But I forgot to say, this is just the kinematic part of that guy, but then there is a loop momentum, an integral associated to this. But what remains true is that the mapping between going from here to there, it's something that you can start even to guess. And that was more or less the approach adopted to compute the two-loop amplitude. You look at the string prescription to be inspired for the things that you need to write down here, the kinematics that you will obtain, and then the idea is that you just need to find an overall BRST invariant quantity once you assign this guy to that loop integral, and you just need to find something BRST invariant. But the idea of finding field theory amplitudes using BRST invariance, I'm going to discuss in the next lecture for tree level only. But the idea is the same. It's if you write something BRST invariant with the correct kinematic poles to describe an amplitude, then the claim is that that's the correct amplitude. And in 10 dimensions, it has worked so far. And as I said, being in 10 dimensions has some advantages because you can study things, you can dimensionally reduce and study lower dimensional guys, amplitudes. But that's the idea, to use string theory as a tool, as a glorified method to compute field theory amplitudes. This is just in the beginning. People know the results for one loop amplitudes up to 6 points, and at two loops 4 points and 5 points. But the hope is that since the expressions that are known so far are very, very intuitive like this, the idea will be to, well, perhaps one can find a generating function for all the amplitudes, just like I'm going to show in the last lecture that has been done for tree level. Tree level, everything is known, and you can dimensionally reduce to everything. But tree level, in some sense, it's simple, but simple things should be simple, and complex things should be possible. So that's the hope.